So now we try to solve problem 6.4, which is a simply supported beam, which means that when we say simply supported beam, it means that one end is in and another end is simply supported, which means that if probably you can use roller, or in this case is a smooth contacting surface, and there are 4 kilonewton loads acting on the beam, which are 1.2 meter apart. Okay, so the question asks to draw the shear and moment diagrams for the beam. Okay, so we follow the procedure. The first one is to draw the outline shape. This is what we call as an outline shape. Don't just draw a single line, right? And then we draw the applied loads, 9 kilonewton, right? 9 kilonewton here, 9 kilonewton there, 9 kilonewton there, and another one, 9 kilonewton, right? And they are 1.2 meter apart from one another. What else we have? We have the reactions at this end, the left end, which is a smooth contacting surface. So we have, let's say, AY, right? Point A. And then at the right end, we have a pin end. So basically, we have this, let's say, BY, and also BX, right? Next, what should we do? We have to find the reaction forces. So in order to find the reaction forces, first of all, one thing is very clear. This Bx is 0. Why? Because there is no other forces in x direction, right? So there is no Bx. So how to find Ay and By? So we need to do you can use whatever thing that you think is correct, right? But one thing that we have learned in statics is that you can do the moment about A or B. Let's say this is point A or point B. You can do at moment about any of these two. If you do moment about point B, you will find Ay, because you eliminate the unknown By here. If you do moment about A, you will find By, because you eliminate Ay on that. Okay. So let's say we want to find Ay first. So we do the moment about B. Moment about B, assuming clockwise direction as positive. So moment about B equals to 0, right? So Ay times, okay, one thing. We need to put the dimensions, alright? So 1.2 meter here, 1.2 meter here, 1.2 meter here, 1.2 meter here, and 1.2 meter here, and 1.2 meter here, right? So Ay, what is the arm distance between Ay to B? So 1.2, 1, 2, 3, 4, 5 times 5, isn't it? So it is 6 meter, right? Plus, because it causes the clockwise rotation, alright? Then what else? You have minus 9 times 0.2, 0.2, 0.2, 0.2. So you have 4.8, isn't it? For this one, for this load, 9 kilonewton load here. And why minus? Because it causes the counterclockwise rotation here. Okay, this is the load, 9 kilonewton, and this is the arm. Okay, and you curl that one, so this one causes counterclockwise rotation. Okay, and then what else? You have 9 times this 9 times this distance, which is 3.6, right? And then this one, 9 times 2.4, and then the last one, minus 9 times 1.2. Okay, how about By? Again, why we do moment about B? Because we don't want By to appear in this equation. So By times 0, so it's 0, right? There is no moment of By at point B, right? Equals to 0. So if you solve, then you will get Ay equals to 18 kilonewton. Okay. You got Ay equals to 18 kilonewton, and then how about Dy? You just do the summation of forces. Dy equals to 0, Again, you can do to find dy, you can do moment about A, but it's up to you. I mean, whichever way you think is easier. So measure of force is equal to 0. So you have dy, right? Unknown dy. You have positive, okay, going up. Assumption going up as positive. And you have ay plus 18, isn't it? And then you have minus 9 times 1, 2, 3, 4 times 4. Okay, you can write minus 9, minus 9, minus 9, okay, so it doesn't matter. So if you do that, then basically by will be the same as ay, which is 18 kilo Newton. This is my answer, right? Okay, and then after we got ay here to be a certain value, which is 18 kilonewton, and by to be 18 kilonewton. So what we have to find again, we have to draw the shear and force, shear and moment diagrams, right? So next step, we need to do the cut section methods, right, to find the shear force equation and the bending moment equation. How many sections that we need? Here, actually, this is something that we really need to understand. Here we have to cut 1, 2, 3, 4, and 5. There will be 5 sections. 5 sections, alright? The first section will be like this. Okay? You remember that I taught in the class before the MCO, we cut and then we take left or right. Doesn't matter. Here, you cut here. Why we cut here? The thing is, why we cut here is because here we have at A, at the very end, the left end, you have 18 kilonewton support. Okay? And then as you move over there, there will be internal forces and internal moments. Alright? So that's why we cut here to find what will be the internal force at this point. Okay? And then next we need to cut here. Why? Because here, when we take the left part, for instance, this 9 kilonewton will change the value of the internal reactions. You see, interaction means that the internal shear force and internal bending moment, right? So, okay, the first one, cut here. So we take the left portion. The left portion is like this, right? This is A again. Okay, this is 18 kilonewton of AY just now. Okay, okay, we have to cut, and then you see the 9 kilonewton is somewhere here, so we cut before 9 kilonewton, the first 9 kilonewton, 1.2 meter from the left, right? So what do we have at the cut section here? So at the cut section here, we have the internal shear force V and internal bending moment M, right? Why the direction is like this? Shear force going down and bending moment going like that, you know, pointing outwards from the surface. Because you remember the sign convention, the positive sign convention for the beam. If you cut, the positive sign convention of V, if you take the left part, will tend to rotate this beam to be clockwise, right? While on the other hand, for bending moment, it will cause the bottom part to be in tension. The top part will be in, see, top part will be in compression, right? So this is the positive sign convention. And one more, we need to have this X. You can name this as M1, V1, X1, whatever, it doesn't matter. But as long as you do it nicely, then it should not be confusing, right? So what should we do? We need to find this V and this M as function of X, right? So V, okay, so we do so for V, the V1 here will be equals to 18 kilo Newton, isn't it? As simple as that. Is it true? Yes, because if you do summation of forces in y direction equals to 0, then this is what we got. Okay, we want just a single constant value of 18 kilonewton going down, right? How about M1? M1, remember this, when you want to find the internal moment M, always do moment about the point that you cut. See, this is the surface that you cut. Do a point, do moment about this point, right? So if you do moment about that point, so you just assume the counterclockwise rotation as positive, because it will be easier to express M1. So it will be M1 plus M1, and then V1 will have no moment, isn't it? And then you have minus 18 kilonewton times X. It's what, isn't it? M1 minus 18 kilonewton. So this 18 kilonewton will cause moment to be in clockwise rotation. That is to minus 18 x1, the arm, right, equals to 0. So M1 equals to 18 x1, and put the range. Okay, this x1 ranges between 0 to 1.2 meter. Is it okay? 1.2 meter. 0, x equal to 0 to x equal to 1.2 meter, this thing. Alright, so it can be anywhere in between. Okay, so this is the first two equations for the shear force, V1, for the bending moment, M1, in expansion of x1, which is the distance between 1.2 distance from A to 9 km load. Alright, so the next card will be, you have to cut here. Alright, why? Because as you move from 0, x equal to 0 to 1.2, now here, actually this 9 km load will change the dysfunction. Right? So if you cut, you take the left part because that's the wise decision, the wise choice.